Hello, everybody. I mentioned that I would make a video of this for folks that still might be struggling. I'm actually going to cut this video into three different pieces. Um, First, our video is going to be looking at the work that we did on Friday. And second, we'll go ahead and take a look at the two pieces in two different parts for today. One is the data table creation, and then one of those will be the creation of the graphs. So I thought I'd break it apart so you can watch whatever part you might need. So keep those things in mind. What I am looking at right now is a document that I created that has this new scenario on it. So it's not any one of the five or four that I gave to you, five that I gave to you. I'm going to use it to kind of be my jumping off point so that hopefully you can understand how you might interpret yours and make sense of it. So the starting point to this is looking down at these questions in blue that I'm calling preparing for the challenge, right? And those are these ones right here. So the first thing I want to do is I want to read through this scenario and then see if I can plug those in and make sense of it without going too quickly. I'm coming up on my office hours time, so I'll see if I can do this and then get into my office hours quickly here. So this first one starts out, it says the car is at rest to begin with, right, on the left-hand side of the frame. At rest meaning it's not going anywhere. It begins to accelerate to the right, and it accelerates for 1/3 of a second until it's finally going 60 centimeters per second, and then it stops accelerating, and it continues to the right at 60 centimeters per second. All right. So down below, the first thing that I asked us to do was to go ahead and create a quick summary of that statement. So I'm going to go ahead and put in here and say that this is example scenario number 3, because I've done a couple other ones before this. And my summary of this is that my starting velocity, right? My starting velocity is equal to 0 centimeters per second. That was given in the problem, right? And my ending velocity, right? So we could say V F for my kind of final velocity here is equal to 60 centimeters per second. And last, it says that I accelerate for a time of 1/3 of a second. Or if I need to do this in calculator speak, right, we could move it out of the fraction side of things, and we can say that this is 0.3333333. Now, granted, I need to approximate this in some way, so I'm going to go ahead and put it in as 3.33, and you'll see why that matters in just a moment. Down underneath here, now that I've made my quick summary, is that I need to do some basic conversions. And my basic conversions, I have my railroad track method here to go from one to the other, and hopefully that's helpful. It starts off and it says my initial velocity, that's what we're talking about first, is 0 centimeters per second. And my animation studio is in centimeters per frame because I need to talk about that more easily. So what I can do is I can use this railroad track method to say if I have 0 centimeters per second, how many centimeters per frame is that? So I'm going to double click on that. And I can put this in here and say this is 0 centimeters per second. That's what starting point is. This part in the middle is my conversion factor, where it means that my seconds cancel out. Right? But 1 second is the same as 30 frames because there's 30 frames every second. So if I multiply across the top, I end up with 0 centimeters, right? If I multiply across the bottom, I end up with 30 frames. And 0 divided by 30, even though I've got centimeters per frame, 0 divided by anything is 0, which means that my final velocity, my initial velocity in centimeters per frame is 0 centimeters per frame. But that doesn't seem all that hard, so that one should be okay. The next one down, though, it says my final velocity is 60 centimeters per second. And so now I want to come over here and I figure out how many centimeters per frame that is. Same conversion, only this time around I'm going to put 60 up here at the top and I'm going to get an answer down at the bottom. So I'm going to go ahead and go back in here just to help out. And I'm going to start this out and I'm going to put, this is 60 now centimeters per 1 second. So it moves 60 centimeters every 1 second. I'm going to leave these just like they were because this is 1 second is equal to 30 frames. But that means my seconds cancel out, right? So I don't have to worry about seconds anymore. And now I just need to multiply across the top, and I get 60 centimeters because that's all that I've got on the top. Oops. And then on the bottom, I do the same thing, only I'm 1 times 30 frames, and that's going to be 30 frames. But now I've got 60 divided by 30. And 60 divided by 30 is not all that hard, right? 60 divided by 30, if I want to, I can say that's just here equal to 2 centimeters per every 1 frame. All right, so I'm going to save that. And I'm going to come in here and I'm going to go ahead and type in 2 centimeters per frame. So this is my final velocity. My starting velocity is here at 0, right? And my final velocity after the acceleration is, maybe I should put that all in red, is equal to 2. Well, down here, we get into, well, how many frames did it take for that to happen? It said up at the top that it takes 1/3 of a second for that to happen. Or we could do this in a calculator if that helps us, 0.333, so, or 0.333 seconds, right? So that would be fine. And I could go ahead and use this frame if I want to, or I could just say, hey, if I put in 1/3 second here and I multiply by 30 frames, 1/3 times 30 is 10. And on the bottom, I still just have 1 second, and the seconds cancel out, and so then I'm left with just 10. But I'll go ahead and do that here if we need it. So calculator speak, I've got 0.333 seconds, right? And my seconds are going to cancel, so this second on the top goes away, and this second on the bottom goes away. Cancel. And now I'm left with 0.333 times 30, and 0.333 times 30 is really 9.99. Oops, not 33, 99. But to be perfectly honest, if this was a true 1/3, those threes would be repeating completely over here, and instead of it being 9.99, you'd actually have 10. Which means that I'm going to accelerate here for 1/3 of a second, and in the world of video, that's a total of 10 frames of acceleration. Right? So now I've got a starting velocity, I've got an ending velocity, and I know that I accelerate for 10 frames. So the next pieces to this are calculating your accelerations and then your positions, which in this case are going to be changes in position, and I ask you to find the position at the end, but we'll get there. So let's take a look at acceleration first. This is a change in velocity divided by a change in time. So let's see if we can make sense of that. I'm going to go ahead and do my math right underneath here. So I could say that A equals, if I'd like, my change in velocity is just how much did I speed up over that piece. And I started at 0 centimeters per frame, and now I'm ending at 2 centimeters per frame. So how much did I speed up? Well, the way to do that, it's pretty easy, but I would take my final and I would just say, hey, I end at 2 and I start at 0, right? That's my change in velocity. And I'm going to divide it by how much time it took for that to happen. Well, in the world of frames, it took 10 frames, and I did that all above, and you can go take a look above, right? So this math is not so hard. 2 minus 0 over 10. This is my change in velocity, 2 centimeters per frame minus 0 centimeters per frame. All over the top of a total of 10 frames that I accelerate. And 2 minus 0 over 10 is also 2 over 10. Or we could simplify that and say it's 1 over 5. Or if we put it into a calculator, we could say that this is 0.2. Any of those things work. This is my acceleration. Oops, I get everything red if I'm not careful. Now, if I wanted to put this in kind of more physics speak, I need to think about this in terms of units, and the units work out just fine. This is centimeters per frame. Right. This one over here is also in centimeters per frame. Right. And I've got 2 centimeters per frame minus 0 centimeters per frame divided by 10 frames. And when that happens, if I take centimeters per frame minus centimeters per frame, I still have centimeters per frame. Apples minus apples is apples. and then I take divided by 10 frames, and that's where the square comes in. You do not need to square any of these numbers. That's not the way the math works. This square only happens on the frame on the bottom, and it's just a part of the units. So don't let that throw you. All right? So there it is. Last but not least out of these puzzle pieces is to say, okay, so what is the total distance the car travels while it's accelerating? Well, I give you an equation to be able to help you out here. And this equation looks more complicated than it is. We're just going to plug in the things that we know in order to get there, right? The starting point is that this delta x, this little part right there, right, is just, right, that's the total distance. That's the change in position from one place to the other. So I'm just going to say this delta x equals, and then I'm going to plug in the things that I know. 1/2, if I was going to do this calculator speak, I would do this in as 0.5. 1/2 is 0.5. And then I need to plug in what I know for acceleration. Now be careful. You might see this square and say, oh, I think that affects the a, but it doesn't. It only affects the t. So this 0.2 that we got for acceleration is what we're going to put in for acceleration right here. So 0.5 is the 1/2. Acceleration is 0.2. And now I need to put in my t squared. So what am I going to put in for t here? Well, my t is the last frame, right? It's the after we accelerate. So it accelerates for 10 frames. And so what I'm going to put in here is I'm actually going to put in a t of 10, meaning the last frame that it's accelerating. There's my 10 from up above. You saw it before. You can go check if you'd like, right? So here I've got my pieces. It's looking pretty good. If I add on to it these last parts, this vi here is my initial velocity. That's how fast we start going, which is 0. And then the t is the same t that we had before, where in this case it's 10. But this is fine because 0 times 10 is 0, so I don't really have to worry about that all that much. And at this point, I can go ahead and say, okay, fine, let's go ahead and solve this. And 0.5 times 0.2, that's pretty easy. That's 0.1. Let's put that as 0.7 so we don't lose the decimal point. So we'll say this is equals 0.1. And then I want to multiply that times 10 squared, and 10 squared is nothing more than 100. What about this add piece on the end? Do I have to worry about that? Well, 0 times 10 is 0. So no, not really. So my final math side of things is just to say, hey, what's 0.1 times 100? And the answer to that is 10. And this is my final answer. My change in position over that acceleration is 10 centimeters. That's it. So I move 10 centimeters during that entire acceleration. And that's the place I'm going to put my car at the end of the acceleration. Now, I didn't put any units in here. If I did, it starts to look a lot more complicated, and yet it's the same problem. The thing that people often make mistakes on is when they try and see these squares here, or if this is in centimeters per frame squared, suddenly they think that this square here should affect the 0.2, but it doesn't, right? And that same thing goes to for any of the parts. So this is t squared, so that would be 10 frames squared. And you have to square both. In this case, maybe I should put this square outside the parentheses so you know you're squaring both the 10 and the frames. And then this is centimeters per frame, right? And then over here is 10 frames. Now this looks a lot worse than what we saw before, but it's the same. It's the same, only I've just included my units. It's still 0.5 times 0.2 times 10 squared, and that's it. Last but not least, it says, what does the car do after it finishes accelerating? Well, I actually have to look all the way back up at the top to my scenario. And it says, once it stops accelerating, it continues to the right at 60 centimeters per second. And so I'm going to come all the way down here, and I'm going to put that in here. So once it stops accelerating, it continues to the right at 60 centimeters per second, which we now know is 2 centimeters per frame. That's it. All right, this is everything in part 1. Hopefully that was helpful. I'm going to go ahead and stop the video now, and I'll do part 2 as how do we solve the data tables down below. So I hope that helped. Sorry. And I will talk to you in the next one. All right, take care. Bye-bye.